All right, for those that are online, can you hear me okay? Okay, great. And if you have any questions and are more comfortable, just go ahead and put it up in the chat for any questions if you have those online. Okay, so last time we talked about the derivation for the RL circuit. Any questions about that one? Okay, quick review. Capacitor. Okay, so capacitor, very generic statement. What does a capacitor store? Okay, stores charge. Great. And so we think of it like a battery. So because we're thinking about a battery, that's usually voltage. So that's one way to remember the equation that I told you to memorize. Anybody remember that equation? Uh-huh. Correct. So that's the memorization. And so because you are thinking about charge, you're going to differentiate the charge. So that's where dV dt. And then if you're doing the dV dt, it's going to equal the opposite. And then you always use the element value, C. So that's going to be the C capacitor value itself. There. All right, so then that's the capacitor. Oh, the other thing. So if dVc dt equals 0, what does that mean? So it's not been changing in voltage, which means what has been going on with the circuit? Correct. So it's been sitting there, steady state for a while, steady state. So transient means right when something changes, that's going to be a transient response. And then a steady state is after it's sat there for a while. So those two terminologies are going to be ones you're going to hear again and again. So transient is right at the beginning and steady state is after it sat there and no change. Okay, so if this is the case, it sat there for a long time, we have dVc dt, and then IC will go to 0. And so if we were modeling this after it's a long time, what would we model this with? Correct. Open circuit. So I had recommended that you watch that circuit kind of concepts video. If you haven't yet, make sure you watch that. So in that circuit concept, I do some demos that show you about a floating node. So floating node has no current flow through it. So if you break this, you're having floating nodes to it. So that's why there's no current flow. So we're going to model that with an open. Inductor, on the other hand, inductors. Put down here. Okay. An inductor stores what? So the inductor stores.
It stores energy in its magnetic field.
Correct. Energy. And so you think of energy as current. And so this is hard to visualize as a current battery, but it's a current source. And so that's harder to visualize, I know. But with the current, then you know you're going to differentiate the current. And so the equation is going to be what for this one?
But the inductance times the derivative of the current with respect to time is going to be the voltage across it.
Correct. So now when this one has been in the steady state or sat for a long time, and di dt goes to 0, VL will be 0. And so I heard somebody say it. Correct, a short. So that one will be a short. Okay, so now we're gonna look at circuits. So I want to highlight here. So this is going to be what you've seen in the past in, well, I'm gonna copy this over because I like it. Not this one. Actually, one. Okay, so this is kind of that summary: capacitor, inductor. And then in the RC and RL, the one I did in class, I did 0 for 0 to T in that derivation. But a lot of times you can even say T0 to T, and T0 is meaning an initial time. So 0 in our case was an initial time. So the form of the equations are always going to be the same here. You're going to have for an RC circuit, you're going to solve for the voltage of it. So again, it is a voltage battery. So that's when you remember what you're solving for is voltage. And then it's going to be the final plus initial minus final, e to the minus t over tau. And what was tau? Remember that one? Okay, so it's RC for that, but tau is standing for what? Time constant. What does that mean? Anybody want to take a stab at that? Yes.
It's a constant with units.
Uh-huh. So, like usually seconds would be your unit. Okay, so for these circuits, you either have, like you have an initial value and a final value. So sometimes it may charge up to that value or it's going to discharge to that value. It will start out at that value and discharge. So in between those values, if I have something that starts at 0 and goes to something else, what form from this general solution does that take? An exponential, yes. It will charge up to it typically. So this is an exponential form in that description. And what the time constant means is that once I reach 70% or 60%, and accurately it's 67%, but somewhere kind of right around that range is where I say it's fully charged. That time is that time constant value. So if this is that value, that would be your tau value. So whether I'm charging it or discharging it, it's about 67% to be more accurate of when I'm either fully discharged or fully charged. So if I went up to 10 volts here, what would be my time constant here? 6.7 would be this. So that would take 6.7 seconds. In electronics. So when you get to digital, 70% typically. So we usually say in electronics, something that's around 70%-ish is either, like in digital, it will be a 1 or a 0 once it's at that level. So, you know, if it's close to 0 at 0.67 volts, it may be considered a 0. And at 4.67 volts, it's going to be a 1 instead of 0 and 5. So because we're working now with real battery values, voltages, we need to know, like, well, what is still considered a high or a low in digital, or if it's in analog, the steady state values.
So if we're considering like to be a 1, it has to be like 67% or 67 to 100% of our max value.
Mm-hmm.
And to be a 0, it'd be like, in this case, 33 or flat, or
Yeah.
33 is less. What about that middle state? Is that just sort of a limbo area for digital logic.
Yeah, so it's going to, if it is digital logic, it would be, say it's 3 volts and your high is 5 and your low is 0. Then that 3 volts is like questionable, like what is it going to do? That's where we get errors. And it will guess and guess which one it is. And then you need to check with error correction methods to see like, was it really 3 volts and what, and then, you know, what should it have been? So that's where you're getting errors in circuitry when you have that. Any other questions on that? Okay, so that's what the time constant actually means. And then the time constant is calculated by the L over RTH for an inductor. And then this is kind of the way it was written before, which I think is pretty confusing. And so just interpret this, it's exactly the same thing. You're going to have your final state. This would be final. This is considered your initial. And then final, and then tau. And then tau is the RTH times C or L over R. So to find the initial value, we're going to look at circuits that have a switch in them. And what you're going to want to do is redraw the circuits so that they are not confusing, because the switch looks really confusing to every single student. So if you've seen a circuit with a switch and go, what am I supposed to do? You're going to redraw it with either an open or a closed where that switch is. And that one will make more sense to you. Yes.
Sometimes when I've seen some circuits where the switch goes from one part of the circuit to the other,
Mhm.
not necessarily just the open and closed. Do
Yes.
we redraw both of those?
Yep.
Instead of
Separated, yeah. So if it was one way, it would be that section of the circuit. And if it's the other, it'd be that section of the circuit. Yes.
Never.
Okay. So the key here is, when do you determine the initial value? And when do you determine the final value? So those are going to be the keys of what you're going to try and find. Because once we get a final value, initial value, and then we can calculate tau. And tau is going to be done by finding the Thevenin resistance of the circuit. And so those are the 3 things that are going to be needing to be found. Once you find those, then you can just plug them into the general form equation. But it's tricky to find those sometimes. So let's go through some examples. The thing to remember is that the initial time is going to be at 0 plus. So that is really big key. Note that if we find the voltage and we're trying to find the voltage in the end, that's going to be easy because the voltage before the switch is going to have to equal the voltage after the switch. That would be then our initial condition. For inductors, it's going to be the current is going to stay the same. But if we want to find a different value in the circuit, we need to first find either the voltage for the capacitor or the current for the inductor. Okay. So this is an example of such a circuit. So we have a switch here. What this means is that at t equals 0, it has the arrow closing. So that means before 0, it's open, and at 0, it closes. So we're going to redraw the circuit. You redraw the circuit with an open. Let me go copy this so I don't have to write it all. Let's see. Okay. So draw the initial circuit, solve for VC for voltage that is the capacitor, and IL for inductor. So draw the initial circuit. You're going to redraw it with leaving out the switch and leaving out the element. Draw every other circuit element around it, and then determine what is the switch doing and what is the element doing. Okay. So in this case, this would be the redrawing. And then what do we do with the switch? And we're gonna do first 0 minus. So the switch would be doing what in this? It would be open. So I just leave that physically open there. And then we assume it sat there for a long time before the switch. So what do we do with the capacitor when it sat there for a long time? Do what?
Treat it as an open circuit.
Correct. So we're gonna again leave this one open. So this would be our circuit, and then across this is still the VC. So this does not have ground in it. I always like to visually put ground on the bottom or try and put ground where there's the most extraordinary nodes. Okay, or the one that has the most branches off the extraordinary node.
Most extraordinary.
The most extraordinary area, but yes. Okay, so in this case, that bottom one's going to be that also because it has 3 branches off of it, and where on the top it wouldn't have 3. Okay, with this being open, what's the current in here? 0, correct. And so the current in here is what? It's going to be 120 micro, right? Because this is all the same wire. So this is the same. And then with 0 current, that's current also has to go and flow down. So that's also going to be 120 micro. Yeah. What is micro?
Cool.
6. So N is nano. So 9 is nano, minus 9. And then M is what? Milli. And it will be minus 3, correct. So we are trying to find the voltage at this node. And so, as I said, I like node voltage. But in this case, I need to write, okay, so let me back up a second. So node voltage is where if I know a value on the top and a value on the bottom, the difference of Vx here, how do I write that Vx? If I have, so the voltage itself will just be VA minus VB. And then the current is going to be Vx. So I will be Vx over R. So it's always the voltages across the resistance over the resistance in the branch. So that's where the node voltage comes from. So in this case, if I was to do node voltage here, I label this one VC, which is still the same. And I know the current here is what? It's just negative 120 micro. And then I know that there's minus 120 micro down there, but I'm trying to solve for VC. So I want to write that I in terms of VC. So that will be VC minus 0, right? That voltage across it, VC's on the top, and then minus 0 on that bottom over 30K. And so now I can just solve this as VC is 120 micro times 30K. And that is I don't think this is the same problem I have on here. Whatever that is. Oh, there we go. Okay. It is 3.6 volts. Okay, so I could also say, well, I know 120 micro and then Ohm's law, which is I times R, which was 120 micro times 30K is going to be the voltage there too. So either way, if you see it. But if it's not 0 on the bottom, you could do VC minus whatever that voltage is on the bottom over the 30K. Okay, so that is my initial. So remember that VC of 0 minus has to equal VC of 0 plus. And the 0 plus is the initial value. So in this case, it is the same 3.6 volts. So that's my initial value. Doable, right?
Yeah.
Okay,
3.6 millivolts. Because if micro is given to -6, the QO is 10 to the third.
Yeah. it probably is, yes. Thank you.
It should be 3.6 volts because it's 3,600 millivolts.
30, oh yeah, you're right. Because you have the 0 zeros from the other. Yeah, thank you. Thanks, Dave. Okay. It's like I thought I did it right. Okay, so that's our initial condition or initial value, final value. So final is now, where is the switch going to be in the final value?
Close.
So I just draw a wire there. And again, it's been sitting for a long time in the final one. Yep. And again, we find that VC. So in this case, I now have a little bit more complicated circuit. I'm going to again put my ground on the bottom. And I'm going to call this node kind of VX. So that's the node I don't know. If I can find the current in this branch, then I can find VC again by just that current times 30K. Because they're in parallel. Yep. Okay. So I love node voltage. So I write first this current equation. What's that going to be?
That I be X divided
Correct. And then this one. So it's already a current source. So I'm just going to say it's negative because I drew the arrow down.
Oh.
So minus 120 micro. And then this one going through there. Correct. And then I can combine the VX values and get a common denominator. So this becomes 5 over 50K. And then 120 micro, and then this is 50K over 6. And that becomes 0.6 volts. So this is now my final value. I know initial value, final value, and now I just need tau. So tau is always going to be in the final state. So you put the switch where the final value is. So that was where it was closed. And now the Thevenin that I'm finding is where the element location is. I take the element out, and that's my AB value that I'm trying to find. Remember, for a Thevenin, any independent sources, you set them to 0. So if you set a current source to 0, what happens to it?
wire. No, I think it is a short. That's a short. Oh, wait, no, I'm confusing open and short.
You guys are right. You had a good thought, but you guys are right. So yes, it is open for a current source, and that's again floating node. So it becomes a floating node, so the current is open. And then a voltage source at 0 becomes the wire, because you have no change across it. Okay, so remember those. So current source is an open, and a voltage source is a short. And so now we just have resistors here. So I usually draw the pathway. So as I come in from A, I get to an extruder node and it's gonna split. So that means those two pathways are gonna be in parallel because they've split. So now as I go through this, this is in series. So I'm gonna have 20K plus 10K in parallel with 30K. And then that combines again to get back to the B side of it. So you ignore grounds when you're finding the Thevenin because you're looking at the element location itself to find A to B. So this now becomes 30K in parallel with 30K. And you can either put it in your calculator or realize that when you have them equal, that's exactly a half. So 15, oh, these are 30K, sorry. So it becomes 30K divided by 2. Oh my, I just did it again. Okay, 30K, there we go. Okay. All right, so then tau is this 15K times the C value. So I have to go back up to the element and the C value is 10 nanofarad. So 15K times 10 nano is -9, thank you. And so this becomes 150 microseconds. And then my final equation for VC of T is the final value, which was what? I did write it down here. So 0.6, correct? And then initial was 3.6, and then the final was minus 0.6, e to the minus t over 150 microseconds. And then that will be in volts. And that would be my answer. All right, questions? Yes. Sorry, you are, so V. Yeah, this is not, right, okay. So I forgot to do the other step, which is VC is equal to I times 30K. And I in this case is going to be based on VX. So I is VX over 50K times 30K. And that becomes 0.6. Okay, thanks for catching that. I forgot to do that extra step. So this was only VX. And then we needed to use VX to find VC. Yeah. Didn't write that out all the way. Okay, you guys ready to tackle it on your own? Okay. All right, so you guys are going to work on this one. Split off in small groups of 2 to 5 people. So introduce yourselves to your neighbors that are sitting around you. For you that are online, please work together. Yeah, and yes, thank you for catching that. Okay. So for you that are online, you guys can actually draw and annotate directly on the screen if you want. And help each other out to solve that.
You guys
introduce each other. Going with them to introduce themselves. By yourself. No, you guys each other, okay? You were together. You guys work together? Okay. Well,
Yes. All right. Yeah. That's all. Yeah.
you guys wanna work together? Are we ready for? Again, you wanna introduce yourself?
Okay. Let's go straight like that.
Right.
Because-
You guys wanna-
We started it, so dried it.
You wanna join me?
Like, let's see.
Yeah, just introduce yourself. Yeah.
The initial.
Now. The, open.
But like. The 4-0 right after. Zero. Because we're.
Company in the middle. So that's where the second there. That's when the wire has to get it. All right. Once the wire should be. Then drive. So right now, since
So you just know that. No, here for V one, you're gonna need to find. And then you go to.
Right. We know that.
That'd be one. I do not. And then go on, then you're more than also.
Now we can write our.
Because like I did fine in.
Yeah. We want to keep it's why we want to keep differential. Yeah. Dude, yeah, that's. It's so, attendance is mandatory. And you have to clear out notes every single day. That's, you just do it again, that's an example. Don't have to be open plans every day, but it's like far from long videos. So it's like, it should be free once.
Decided to do.
Yeah.
Yeah.
So that's been.
That's what lost me. Yeah. First one, the class is okay. But then it flips to figure out, which I'm also like, this. Some of the vector stuff, like, will be pretty, but that's because you can spend like, oh,
Yeah.
and then it switches back to linear. To different. And it's like, I don't know.
Yeah.
So yeah, just use what you learned in your other. I don't understand it of what I did. I was. Yeah.
Oh, we scout.
The table here, it's focused, but your ECE is still zero because it's so. Does that make sense?
Oh, okay.
A little weird, because like in the fourth zone, it's been the same for a long time, so when that closes, it actually becomes a liquid. So so it'll be,
No, it'll be an open source.
that, yes. So it does become a wire. That's why it like stays zero.
Yeah.
Because it's so there's no charge in it. Okay.
You're right, you're right.
If there's changing. Like, flow, current, there's no charge.
I got it right. I have a copy of this. Yeah, so, all right. Yeah. All right, so point is, I mean, you can go ahead and.
We're bringing this.
Where are you?
Yeah.
This is.
So, yeah, but to be honest, it's probably be fine. All right. So let's.
So we talked.
Right. So
They're gonna be the same.
Kill one right there, okay, and then our in voltage we select plus 13. No, 14. Yeah. So, and it's just, it's really, you have to find it in a few different states. Earlier last year, the actual state, what we had, the sun short out. And you have to take some of the year. Lost rights can't get there. Either, so the mom of the hero. Yeah, we got on the finance, so we don't get
All right, so
So do that, you just do a provider, you bring the whole first. And then you, that equation that you're looking at. Once you have the initial. The initial right there and the final, function subtract from it, and then you just do it. And then. And I just found this. Oh, I'm wrong with that.
Okay, so initial value, switch is going to be open, VC or capacitor will be open too. And then with no source in there, because they're disconnected, then you have current is 0 because it's a floating node now. And so your voltage has got to be 0 if your current's 0. So VC will be 0 in that case. Note that V1 is equal to VC, so that will be the same value for the initial value for V1. So we can just write VC and then V1 is in parallel to that. So it's the exact same. The final, you can note that that's a current, or not a current, a voltage divider. But I hate to tell students to do it that way because you're going to mess up sometimes with remembering that voltage divider equation. So I say always use node voltage instead, and that will get you to the right answer. So node voltage in this case is going to be, I called the top one VC. So this is all the same wire. So this is my VC, and I put my ground on the bottom. And so the voltage across the 2K resistor, one side's VC, and I take the plus side of the current first and then subtract off the minus side. So with the arrow being drawn in this direction, I draw my arrows outward always because I want to do a KCL summation of them always just plus, plus, and plus. But you can draw your arrow any way you want and then describe the current going in the direction of whatever way you label your arrow. You start at the plus side and then you subtract off the arrow side. So in this case, VC minus 20 over 2K, and then solve that, it ends up being 40 over 3, which is approximately 13.33. And then for tau, what do I do with the switch for tau? Which position? Okay, because it's the final position. So always, this is the common mistake I see students forget to say which circuit do I want to have for the final state. So, or which circuit do I use for finding tau? It's always at the end when it's at steady state. So close this, and then this is my A and B. And then what happens here? It acts as a short. So then I have the pathway goes and splits, which is a parallel. So I have RTH is 2K in parallel with 4K, which ends up being 4/3 K. And then V1 is equal to VC. So it's final, which is 40 over 3, and then initial was 0 minus final, E to the minus T. And tau is 4/3 K times 2 micro. And that is my answer for B1.
What does that come up to, the 1/3 K times 2 micro?
8 over
3.
8 over 3 milli.
What are the units for that? No units, right? Units.
Seconds. Yeah, it's still in seconds. All right, questions? Okay, so this Friday I have a family situation, and so we will not have in-person class. I'm going to post some video solutions to the next couple problems. So No worries about coming to class on Friday. So do watch for those videos. They'll be on the lecture page and they'll be like problem and then video solution, problem and video solution. So work through those video or through the problems. And then that is going to be, this is what your homework is for next week, is solving an RC circuit and an RL circuit. And then your quiz will be RC or RL. It will pull both. So that's basically what we're going to do, is start just practice for RC and RL, and then we'll move to RC, LC next week. All right. All right, thank you.
I know. Permitted for my office hours, I was appreciating because sometimes I finished just a couple of questions. I already got it. Okay. Right now, I have 5 to 6 hours of it, so they can What's the other camera? You take my. But.